Welcome to The Explainer. Today, we're diving straight into something that is, frankly, a little unsettling. We're going to explore the hidden and sometimes genuinely dangerous vulnerabilities of computer vision. We're going to see exactly what happens when the artificial intelligence systems that we blindly trust to see the physical world for us suddenly go blind. So, how does a self-driving car mistake a school bus for an ostrich? I know, it sounds like a punchline to a bad joke, right? But this is actually a startling, real-world scenario documented in recent AI research. We're increasingly relying on machine vision for our everyday safety, yet these incredibly advanced systems can fail in ways that just completely defy human logic. To figure out why this happens, we kind of need to look at how we see the world versus how these machines do. And honestly, this comparison totally shatters the illusion that AI is perceiving the world the way we are. See, human vision relies heavily on global shape and context. We instinctively filter out complex or irrelevant data. If a stop sign is covered in a bunch of graffiti, you still know it's a stop sign, right? Machine vision, on the other hand, gets completely hung up on tiny mathematical deviations. It relies strictly on pixels, textures, and algorithms. Section 1. How AI actually sees. There's this quote from a research team at UC Riverside that really hits the nail on the head. They noted, computers see with a kind of tunnel vision that leaves them vulnerable. And that perfectly frames the problem we're dealing with. The human brain can process multitudes of data and past experiences simultaneously to make a safe decision. Computers just lack that infinite, instantaneous complexity. They're constrained entirely by math and whatever was in their training data sets. The absolutely crucial point here is a concept called visual texture bias. Basically, this is the prioritization of local, pixel-level textures over global structural geometry and shapes. While you and I rely on the global shape of an object to instantly know what it is, the AI is hyper-focused on local micropatterns. If the background texture changes or the pixel pattern is altered even slightly, the AI is completely lost, even if the overall shape is perfectly clear to us. Section 2. The shortcut learning problem. Okay, have you ever heard of the clever Hans effect? It's this fascinating biological parallel that perfectly illustrates our AI problem. Clever Hans was a horse, and people genuinely believed he could do complex math. But in reality, the horse was just responding to superficial body language cues from his trainer to know when to stop tapping his hoof. Well, AI does the exact same thing. Deep neural networks minimize loss by taking the absolute easiest path. They optimize for mathematical efficiency rather than logical correctness. So they're basically just responding to superficial cues instead of actually learning the task. So let's break down exactly how these shortcuts actually show up. There are basically two main types here. First, you have instinctive shortcuts. The primary mechanism for this is biased data during the model's pre-training phase, like an AI just predicting high-frequency words rather than actually learning logical relationships. Second, you have acquired shortcuts. These are learned superficially during context processing. A good example is an AI mapping a label to a physical token's position on a page, rather than understanding the semantic meaning of it. When systems learn these bogus correlations, they become highly vulnerable the second you take them outside their static training environments. Section 3. Anatomy of adversarial attacks. Right, so what happens when a malicious actor actively weaponizes this? That is an adversarial attack. These are carefully crafted inputs designed to manipulate a model into producing incorrect outputs, all while remaining completely visually imperceptible to humans. Think about the gravity of that for a second. These attacks can systematically fool state-of-the-art vision models, and to you or me looking at it, nothing looks out of the ordinary at all. It raises absolutely zero suspicion. And these attacks have basically evolved across three specific domains. First up, pixel space attacks. This involves adding invisible digital noise to an image. You can't see it, but it completely blinds the AI. Second, you have physically realizable attacks. This is where it bridges the digital and physical worlds. We're talking adversarial patches, stickers, or even 3D wearable textures. And third, latent space attacks. These go even deeper by manipulating the high-dimensional internal semantic representations of the model itself. Now, you might be wondering, why is this such a massive security concern? Well, it's because of the danger of transferability. Basically, attacks designed for one specific task can automatically compromise completely different ones. If an attacker designs an invisible perturbation just to fool an image classification model, that exact same attack can automatically compromise object detection and segmentation models too. A single vulnerability can easily cascade across multiple computer vision tasks. Section 4, real-world physical threats. 6 meters? I mean, think about that for a second. That is a massive distance when you're cruising down the highway. But this number actually represents the depth perception error an attacker can induce in an autonomous driving system using just one specially optimized patch. By targeting a vehicle's monocular depth estimation technology, a simple printed sticker can make a self-driving car misjudge an obstacle's distance by up to 6 meters. What's wilder is that attackers don't even need to touch the objects they want the AI to misclassify. This is called a context-aware attack. Step 1, they target a multi-object scene. Step 2, they introduced an out-of-context background object. Step 3, the primary object gets misclassified. By simply manipulating holistic scene relationships, literally just placing a weird object in the background, the attacker easily fools the victim model without ever altering the primary target itself. Section 5, Consequences and Future Outlook. When you start looking at the real-world consequences here, it gets pretty sobering. We're looking at autonomous driving safety hazards where a mere sticker on a stop sign can cause a crash. We're talking about medical imaging misdiagnoses, where imperceptible digital noise completely alters an X-ray result. Then there's financial fraud bypassing security and biometric authentication failures where facial recognition is easily tricked. Objectively speaking, these are severe, systemic vulnerabilities across some of our most critical sectors. And the thing is, this threat is just getting faster and stealthier. We're now seeing the rise of zero-query attacks. This means modern attackers can exploit those contextual relationships we talked about earlier to launch rapid attacks without risking detection. They don't even need to probe or query the victim's software to succeed anymore. They just need to understand the visual context, and they can break the system entirely from the outside. So, I want to wrap up our explainer today by leaving you with this thought. If our most critical infrastructure relies on a vision system that can be fooled by a simple printed sticker, who is really behind the vehicle? Take a moment to think about our growing reliance on these fragile, texture-biased systems and what that actually means for the future of artificial intelligence in our daily lives. Thank you so much for joining me, and I hope this changes how you view the machines that watch our world.